All right, let's dive into a story you wouldn't expect. Picture yourself. You're at the pub. You order a Guinness.
Classic.
Yeah, you're expecting that perfect pour, the creamy head, that taste that's always the same.
Yeah.
Delicious. But have you ever stopped to think about like the science behind that consistency?
Oh, yeah.
Well, today we're going to uncover how that quest for a perfect Guinness actually led to one of those important tools in science, the t-test, or the t-test, sometimes you hear it.
Yeah. It's a pretty amazing story. We're going all the way back to the early 1900s.
Uh,
Guinness is already, the world's largest brewery. They're expanding like crazy globally. And to keep that quality top-notch on such a massive scale, they brought in a team of brilliant scientists.
so they had scientists looking at like everything from the barley they used to like how sweet the malt extract should be or
Yeah. Oh, yeah, absolutely. It was a real hotbed of research, lots of experiments going on. And that's where our kind of unlikely hero, William Sealy Gosset, comes in. Mathematician turned brewer.
a mathematician turned brewer.
Okay.
Now I'm intrigued. What was the specific challenge that kind of led Gossett to this breakthrough?
Well, one of the biggest hurdles for Guinness was hops, that key ingredient that gives beer that bitterness and helps preserve it. So brewers, they needed to measure something called the soft resin content in these hops, and they were aiming for around 8%. Now imagine, testing every single hop flower from a massive crop.
Yeah, not really practical.
No way. So they relied on random samples, just like, scientists do in all sorts of experiments today.
Yeah, makes sense.
But that's where things got a bit tricky. Let's say they took a sample, measured the soft resin, and it came in low, like 6%. Did they reject the whole batch of hops based on that?
Well, that's a tough call. I mean, it could have just been a fluke, right?
Yeah.
A bad sample.
Yeah, exactly. It could be that the whole crop was bad or they just got unlucky with a sample that happened to have low resin. And this uncertainty, it's not just a brewer problem. Scientists across all kinds of fields, they deal with this all the time.
So how did Gossett tackle this problem of uncertainty, especially when you don't have tons of data to work with?
Well, before Gossett came along, statisticians, they mainly worked with large samples. Those tend to behave in more predictable ways. But small samples, it's a whole different ballgame. And Gossett realized that the statistical methods they had back then, they just weren't good enough for analyzing these smaller data sets.
Okay, so he's working with these smaller data sets. What's his goal? What's he trying to figure out?
He wanted to figure out how to determine what we call statistical significance, even with limited data. In other words, how likely is it to get a result, like that 6% resin sample, if the true average is actually 8%? If it's really unlikely, then the difference is probably real, not just random variation.
I see. So it's about telling the difference between a genuine difference and just like a random blip, especially when you're working with just a small amount of data.
That's it, exactly. And this is where the signal-to-noise ratio comes in. The signal, that's the difference between what we actually see in our sample and what we expect, in this case, that 2% difference in resin content. The noise, well, that represents just the natural variation you'd normally expect to see in hop resin levels.
So a high signal-to-noise ratio, that means the finding is more likely to be significant, not just random noise, right?
Exactly. Gossett, he was basically trying to figure out how strong does that signal have to be to really stand out from the noise, especially when you're dealing with these small samples.
And this is where he had his big breakthrough, I'm guessing.
You got it. Gossett spent ages painstakingly calculating these new statistical distributions, specifically for small samples. And we call these t-distributions now.
Okay, t-distributions. And how are these different from that standard bell curve, the one we always see in stats?
The big difference is t-distributions, they have what we call fatter tails. This basically means that to be really confident in a result from a small sample, you need an even stronger signal for it to be considered statistically significant. And that's the heart of the t-test.
So it's like a way to cut through all the uncertainty and figure out if a result is really real or just a fluke, even when you don't have a ton of data to work with. That sounds incredibly useful, especially for researchers working with limited sample size.
That's it. And think about it. Gossett, he did all this while working at Guinness. He actually published his findings under a fake name, Student, to protect the brewery's secrets. That's why it's often called student's t-test.
That's amazing. He was like making groundbreaking statistical discoveries in his spare time while also running the brewery's research.
It's pretty wild. And his work, it completely changed science, way beyond brewing. Think about medical research, economics, psychology. They all rely on the p-test to make sense of data and draw real conclusions.
It's amazing how something that started as a quest for brewing consistency led to such a powerful tool with such wide applications.
Ah.
So next time we enjoy a perfectly poured Guinness, I guess we can raise a glass to William Sealy Gosset, the brewer who gave us the two test.
Absolutely. His work shows us that groundbreaking innovations can come from, well, pretty much anywhere. Yeah, it really is remarkable how, trying to make a perfect pint of beer could actually lead to this huge change in how we do scientific analysis.
You say it revolutionized science, but can you break it down like WHY? Is it so powerful? How do researchers actually use it, out there in the real world?
Okay, sure. Let's imagine we have a medical researcher testing a new drug, maybe for high blood pressure. So they've got two groups, right? One gets the drug, the other gets a placebo. After a few weeks, they measure everyone's blood pressure.
And let's say the group that got the drug, their blood pressure is a bit lower
Yeah.
on average. But is that difference enough to say, okay, this drug actually works?
That is the million-dollar question. And that is exactly where the test comes in. It helps us determine if that difference in blood pressure is statistically significant, which means, is it unlikely to have happened just by chance?
So the t-test helps rule out the possibility that the difference we see is just a fluke, just random.
Exactly. It gives us a way to quantify how confident we are in the results. And the way it does that is by calculating what we call a p-value.
Oh, right. You mentioned the p-value before. Can you remind us what that actually represents and how do researchers use it?
Sure. The p-value is basically like a probability score. It tells us how likely is it to get the results we got, or even more extreme results if there's actually no real difference between the groups we're comparing.
So if the p-value is very low, that means it's probably not just random chance that we're seeing this difference.
Exactly. In science, we usually use a cutoff of 0.05 for the p-value. So if the p-value is less than 0.05, that means there's less than a 5% chance of seeing those results just by luck. So we consider that statistically significant.
It's like a benchmark for saying, okay, this probably a real effect, not just noise.
Yeah, exactly. And the cool thing about the t-test is it takes into account, a bunch of factors like the sample size, how much variation there is within the data, and the size of the difference we're seeing.
So it's a much more sophisticated analysis than just saying yes or no. It gives us a deeper understanding of how strong the evidence really is.
That's a great way to put it. And that's exactly why the t-test is so widely used across so many different fields of science. And it's not limited to just comparing two groups, like in our drug trial example. We can also use it to test if a single sample is significantly different from some known value.
So can you give an example of that?
Sure. Going back to our Guinness example, let's say the brewery wants to know if a new batch of barley they got has a significantly different starch content compared to their usual standard. They could use a t-test to compare the starch content of that new batch to that known standard.
That makes sense. Or like in psychology, researchers could use a t-test to see if people's reaction times are faster after drinking coffee compared to a control group that didn't have any.
Exactly. The possibilities are almost endless. And to think, it all goes back to William Gossett and his quest to make sure that Guinness was always perfect.
It's amazing to think that he probably had no idea how influential his work would become.
It just goes to show, the power of curiosity and
Right.
really digging to a problem. Brewers, just like scientists, they have to be super meticulous. They have to understand variation and make sure the quality of their product is spot on.
So when we enjoy a perfectly poured Guinness, we're not just tasting, a great beer. We're also tasting the legacy of this statistical pioneer who helped us understand the world in a much more precise way.
Couldn't have said it better myself.
How about?
It's a great reminder that sometimes the most important discoveries come from tackling these seemingly everyday problems.
Now, knowing how important the test is and how widely it's used, are there any potential pitfalls, things to be careful about when using it?
That's a great question. It's really important to remember that the test is a tool, and like any tool, it can be used well or it can be misused. There are certain assumptions it makes and certain limitations we need to keep in mind.
Can you talk about some of those key considerations?
Sure. One important assumption is that the data we're analyzing follows a normal distribution, that classic bell curve shape we mentioned earlier. If the data is skewed or has a lot of outliers, the test might not be the best tool for the job.
So if the data doesn't really fit that bell-shaped pattern, other statistical tests might be a better fit.
Exactly. And another important thing to remember is that the TD test tells us about statistical significance, but it doesn't necessarily tell us about practical significance. So we might find a statistically significant difference between two groups, but if the difference is tiny, it might not actually matter in the real world.
So even if a difference is technically significant,
Hmm.
statistically speaking, it doesn't necessarily mean it's meaningful in a practical sense.
You got it. We always need to consider the context, the size of the effect, and what it really means in real world terms. And another key point is that correlation doesn't equal causation.
Just because we see a statistically significant difference between two groups doesn't automatically mean that one thing caused the other. Right.
Right. There could be other factors at play that we haven't even considered. The t-test is a great tool for finding potential relationships in data, but it's up to us to interpret those relationships carefully and not jump to conclusions.
So the t-test is more like a starting point for investigation, a way to pinpoint areas where we need to dig deeper, but it's not the be-all and end-all answer to every research question.
Exactly. It's one piece of the puzzle. We need to be aware of its assumptions, its limitations, and always try to use it responsibly and ethically.
It really sounds like the t-test is a powerful tool, but it's not something we should just blindly apply. We need to understand its limitations, its strengths.
Yeah, for sure. For sure. Statistical analysis, it's a bit like detective work, right? You
Okay.
know, you're using these tools to uncover clues and build a case, but you got to always consider other explanations and be careful not to jump to conclusions.
Makes sense.
Yeah.
It is fascinating, though, how this simple quest for a consistent pint of Guinness
Mhm.
led to this huge change in scientific thinking, right? William Sealy Gosset, or student as we know him in the stats world, he really left a remarkable legacy.
Oh, absolutely. It really shows us that innovation can come from anywhere. You know, sometimes the most groundbreaking stuff comes from tackling these everyday problems that we all face.
Yeah. Not all scientific breakthroughs happen in these fancy universities or high-tech labs, right?
Mhm.
Sometimes
Mhm.
they happen in a brewery, driven by this desire for quality and a thirst for knowledge, I guess.
Well said, well said.
Gosset's story. It also shows how important it is to do these small but well-designed experiments. He didn't have access to these massive data sets, right? He had to rely on careful observation, meticulous data collection, and of course a brilliant mind to come up with this method that revolutionized data analysis.
You hit the nail on the head there, and it's incredible how his work, which started with this focus on brewing, has now spread to pretty much every field of scientific research you can think of.
Really is. It speaks to this interconnectedness of knowledge, right? A solution developed for one specific area can have these huge implications in completely different fields.
Mhm.
The tight test is just a perfect example of that. This cross-pollination of ideas.
Couldn't agree more.
Speaking of connections, I came across this interesting observation by John D. Cook. He's a mathematical consultant. He was talking about why the tight test, might have come from a brewery as opposed to, say, a winery.
Oh, that's interesting. I've never thought about that. What was his take on it?
Well, Cook basically said that brewers, by their very nature, they strive for this consistency. Their goal is to produce a beer where every batch, every pint tastes the same, right? They want a standardized product that they can replicate over and over.
Right, right. As opposed to winemakers who often, embrace the variations between years and bottles, right? Those subtle differences are part of what makes each vintage unique, part of the charm, I guess.
Exactly. And Cook suggests that this inherent focus on consistency in brewing might have actually been a driving force behind the development of the t-test.
Yeah.
It was a tool that was born from this need to understand and control variation,
Yeah.
to make sure that every single point of Guinness met a certain standard.
That actually makes a lot of sense. I mean, if you're trying to make a product that's perfectly replicable, you need really rigorous methods to measure those subtle differences, right?
Right.
And to be sure that they fall within an acceptable range.
Yeah, for sure. And the t-test, it provides this framework for quantifying those differences and figuring out if they're truly meaningful or just random fluctuations.
Absolutely. So the next time you enjoy a perfectly poured Guinness, remember that you're not just tasting a delicious beverage, you're also tasting the legacy of a statistical revolution, a revolution that started with this quest for consistency and precision.
It really is a reminder that science is all around us, often hidden in these everyday things, and that even a simple pint of beer can hold the key to groundbreaking discoveries.
Well said. Cheers to that. And to William Sealy Gosset, the brewer who showed us how to see the world through this lens of statistical significance.
Cheers indeed. This has been a truly enlightening deep dive.
Yeah.